Hey, what is up guys? Welcome to another video. In this video I'll be talking about vectors. I want to talk briefly about what vectors are, and then I'll be going through some problems involving vectors. So in mathematics, if I were to state what a vector is as simply as possible, I would say it's a straight line with a direction. Now we know that a straight line has a length. In terms of a vector, we would say that's its size or its magnitude. So a vector has a magnitude, which is a fancy word for size, and it has a direction. So we're adding that extra dimension or extra complexity there by giving this line a direction. So I want to give a brief example of how we use vectors, because thinking about vectors in terms of mathematics can sometimes be quite difficult, but if you think of the applications of vectors, they begin to make more sense. So one application of vectors is describing forces in the world around us. So if you were to pick up a ball and throw it, you would be putting a force on that ball. So let's say you threw it through the air with some force. We could describe that force with a vector. So not only does it have a direction, the direction you're throwing the ball in, it also has a size or a magnitude of the force you've thrown the ball with. So the ball is now flying through the air, and you know it's not going to fly forever. It's eventually going to hit the ground, and that's because of gravity. So gravity is pulling the ball towards the ground. And we can also represent gravity with a vector. So that's going to be a vector pointing straight down to the ground, and also the size of that vector will represent the size of the gravitational force acting on the ball. And another useful thing we can do with vectors is to say that, well, if we throw this ball with a certain force, and there's also gravity acting on the ball, we can add those two vectors together to find the total forces acting on the ball. So that's one application of vectors. There are many others, but in mathematics, we generally are just looking at vectors by themselves without any kind of context. So that's why I say in mathematics it's a straight line with a direction. And the length of the line represents the magnitude or the size of the vector. So let's talk about some notation. So we could have a vector starting at a point, let's say A, and ending at a point B. One way to write this vector is A, B with a little arrow on top. So that's saying the vector is going from A to B in this direction. Another way to describe vectors is we can label them. So we usually label them with a bold letter. Now it's a bit difficult to write bold letters in handwriting, so sometimes you might see vectors written with a little hat on top. So that's another way of describing vectors. We can label them with a bold letter, and so the usefulness of this is just to make it easier to write. So instead of having to write AB with an arrow, I can just write a little a. Another way of describing vectors is with what we call column vectors. So this is similar to coordinates, so we call this a column vector. So let's say to get from A to B, we need to go horizontally 5 units and up 4 units. So the column vector, the top number represents the horizontal movement and the bottom number represents the vertical movement. So that's another way of describing vectors with a column vector. And we can also multiply vectors to make them larger or smaller, which is essentially saying we are increasing the magnitude. So we can increase the magnitude by multiplying the vector, and we usually call that a scalar. So we can increase the size of vectors by multiplying by a scalar. And another application of vectors, as I said before, is we can add and subtract them. So if I had another vector here going from B to C, we can add those two vectors. I could label this vector B, and I could say A plus B, and I could work out what that new vector is, and that vector would go from A to C. So A plus B would be the vector AC, and I could label that C. So we can add vectors, we can also subtract them to find new vectors. So that's a very brief introduction to vectors and the kind of notation we use with vectors. But don't worry if that was all a bit too much. We'll go through some questions and it will start to make more sense as we go through the answers. So let's go ahead and get into some questions. Alright, the first question is a 5-mark question, and it gives us three vectors. Vector A is 5, minus 2, vector B is 1, 7, and vector C is minus 7, 0. And part A says write as a column vector 2A. So this is asking us to multiply the vector A by 2. And all we need to do to multiply a vector by a scalar is to multiply each number in that vector by 2. So 5 times 2 is 10, and minus 2 times 2 is minus 4. So that will be 2A. Part B says write as a column vector 3B minus C. So here we need to multiply B by 3 and then subtract C. So 3 lots of B will be 3 times 1, which is 3, and 3 times 7, which is 21. And then subtract C, which is minus 7, 0. So 3 minus 7, that's 3 plus 7, so that's 10. And 21 minus 0, that's 21. So 3B minus C will be 10, 21. Part C says work out the magnitude of A, give your answer as a surd. So to work out the magnitude of a vector when we're given it as a column vector, we can draw that as a diagram. So remember, the top number is a horizontal movement, which is 5, and the bottom number is the vertical movement. If it's a negative, it's down, so that'll be a negative 2. And the vector A is going from this point here to the end of this line over here. So this is A. So this is a right angle triangle, and we need to find the hypotenuse of that right angle triangle. How do we find a hypotenuse? We use Pythagoras' theorem. So we can say A will be the square root of 5 squared plus 2 squared. We can ignore that negative because we're squaring it, so we don't really need to write the negative. So this is going to be the square root of 25 plus 4, which is the square root of 29. And that is the magnitude of A, or the length of A. Question 2 says ABCD is a parallelogram. BC, the vector BC equals 5 minus 1, and the vector DC equals minus 2, 3. And we need to find the vector BD as a column vector. So here we have BC and DC, which is going in this direction. BC is going in this direction. We need to find BD. So here we need to add the vectors, but before we can add them together, we need to find the vector CD, because they've given us the vector DC, which is going in the wrong direction. So CD is going to be the opposite of DC. In other words, just the negative of DC. So we take these numbers and we change the sign. So the negative of minus 2 is 2, and the negative of 3 is minus 3. So now I have the vector CD going in this direction. So now I can add BC to CD to get the vector BD. So BD is going to be 5 minus 1 plus 2 minus 3. And to add column vectors, we can just add the numbers. So 5 plus 2 is 7, and minus 1 plus minus 3, that's minus 4. So BD as a column vector will be 7 minus 4. Question 3 says A is the point with coordinates 2, 3. The vector AB equals 5 and minus 4. Find the coordinates of B. So A is at a point 2, 3. And we need to go across 5 and down 4 to get to B, and this will be B down here, and we need the coordinates of B. All we need to do to find the coordinates of B is to add 5 and subtract 4 from the x and y coordinates. So 2 plus 5, that'll be 7, and 3 minus 4, that would be minus 1. So that's how we find coordinates using vectors. Question 4 says the diagram shows a trapezium ABCD. The vector BC equals 2AD, the vector AB equals X, the vector AD equals Y. Find in terms of X and Y the vector AC. So the vector AC is here. And well, if BC equals 2AD, that means that equals 2Y. So AC is just going to be X plus 2Y. Part 2 says find the vector DC. So that's going to be here. So to get from D to C, we could go from D to A and then A to C. Now to get from D to A, that's going to be minus Y. So DC is going to be minus Y plus AC, which was X plus 2Y. And then we can simplify this, so minus y plus 2y, that will be y, so DC is just going to be x plus y. Part B says the point E is such that AE equals x plus y. Use your answer to parts A2 to explain why AECD is a parallelogram. Okay, so AE equals x plus y. X plus y will be here somewhere. Let's just rub that out. So E is going to be about here. So that's y in there. And we need to explain why AECD is a parallelogram. Well, remember that DC also equaled x plus y. So AE and DC, those vectors are equal, so they must be parallel. That's another property of vectors in that they don't have a position. So we can say that the vector AE actually equals the vector DC. Even though they're in different positions, they're still equal as vectors. So that can be the first line of our explanation. We can say that AE equals DC. So therefore, they have the same direction because they're equal. And vectors with the same direction, they must be parallel. So therefore, they're parallel. We also know that BC and AD must have the same direction because BC is just two lots of AD. So we can say that BC and AD are parallel. So BC equals 2AD. So therefore they have the same direction and therefore they're parallel. And we don't actually need to say the lines are equal because we've already proved that these two lines have equal length. So these two lines here must have equal length. So that's all we really need to say. So therefore AECD is a parallelogram. So to prove something is a parallelogram, you only actually need to prove one set of lines are equal and the others are parallel. So that was question 4 for 4 marks. And now I want to go into some exam style questions. Okay, so here's the first exam style question. And this question says OAB is a triangle. P is the point on AB such that AP to PB equals 5 to 3. OA equals 2A. OB equals 2B. OP equals K bracket 3A plus 5B, where K is a scalar multiple. Find the value of K. Okay, so they give us this vector OP and they're asking us to find K. Well, to find K, we need the vector AP. And to find the vector AP, I need the vector AB. So what will AB equal? Well, let's start with that. So the vector AB, that's going to be 2B. That's the vector 2B here. And then I can subtract the vector 2A to get back to B. So that will be minus 2A. So I can say the vector AB will be 2B minus 2A. And then I know that the line AB is split up into this ratio 5 to 3. So that will be 8 parts in total. And I know that AP is 5 lots of those parts. So AP is 5/8 of AB. So I can find the vector for AP, which will be 5/8 of AB, which was 2B minus 2A. Okay, so now I have a vector for AP. Now I can find a vector for OP. So I can say OP will be OA plus AP. So OA is 2A plus AP, which is 5/8 2B minus 2A. And then I can go ahead and simplify this, and hopefully I'll have some factor which I can say equals K. So let's go ahead and simplify. This will be 2A plus, now 5/8 times 2. I can cancel the 2's. So this becomes 5 on 4B. Again, this will be 5 on 4A. And then I need to do 2 minus 5 on 4, or 2 minus 5 on 4. That's the same as saying 2 minus 1 1/4. 2 minus 1 is 1, and 1 minus 1/4 is 3/4. So this simplifies to 3/4 A plus 5 on 4B. And then I can factorize out the common factor, And can you see the common factor of this expression here? It is a quarter. So if I take a quarter out of 3/4, I'm left with 3. So 3a, and a quarter out of 5 on 4, I'm left with 5b. And so now I can say OP is a quarter times 3a plus 5b, and we were looking for that factor there. So here I can say that k equals a quarter. And that was a question worth 4 marks. The last question I want to go through is a 5-mark question, and it says two vectors are defined as follows. The vector AC equals -2, -1, and the vector AB equals -1, -4, and it says find the value of the cosine of ACB in its simplest form. Well, the first thing we have to do is actually set up kind of a diagram to picture what angle we're actually looking for. So if we put the point A down, so if this is A, then AC, well, I need to go along -2 and down -1. So C is over here somewhere, and that will be the vector AC. And B will be -1, -4 away from A, so B is going to be down here somewhere, and that will be the vector AB. We're looking for angle ACB. So to find that angle, I need to connect C and B to make a triangle, and that angle is going to be in here. So that's angle ACB. So to find the cosine of an angle, I need some sides of this triangle. So how can I go about finding the lengths of these lines? Well, I can use the same method as I used in the first question, which was Pythagoras' theorem. So I can represent these vectors as hypotenuse of right-angled triangles. So if I were to draw this as a right-angled triangle, this leg would be 2 and this would be 1. So I'm taking those numbers from these column vectors up here. And if I were to draw this vector as a hypotenuse, then this leg would be 4 and this one would be 1. So I can find the lengths of these lines using Pythagoras' theorem. So AC will be the square root of 2 squared plus 1 squared, which is 4 plus 1, and so that's going to be the square root of 5. AB will be the square root of 4 squared plus 1 squared. So that's going to be 16 plus 1, which is 17. So this is the square root of 17. And then I need CB as a column vector. So to find the vector CB, I can use the negative of AC, so going back this way, and then add the vector AB. So to find the vector CB, I want the vector CA, and then add the vector AB. So as I said previously, if I want the negative of a vector, I can just change the signs on these numbers. So CA is going to be 2, 1. And then I can add AB, which is -1, -4. And so 2 minus 1, that's 1. And 1 minus 4, that's -3. So the vector CB can be written as 1 minus 3. And so now I can find the length of CB, which will be the square root of 3 squared plus 1 squared, which is 9 plus 1, which is the square root of 10. So now I have all the lengths of this triangle. So AC was the square root of 5, AB was the square root of 17, and CB was the square root of 10. And to find the cosine of that angle, I can use the cosine rule. So the cosine rule says a squared equals b squared plus c squared minus 2bc cosine a. And I can rearrange this to make cosine the subject of this formula. So the first thing I'll do is to add this to the other side. So this is going to be a squared plus 2bc cosine a equals b squared plus c squared. Then subtract the a squared, so I get 2bc cosine a equals b squared plus c squared minus a squared. And then divide by 2bc to get cosine a by itself. So the cosine a equals b squared plus c squared minus a squared divided by 2bc. So you've probably done that before, you've probably rearranged that formula before to get cosine by itself, but I thought I'd just go through the method just in case you haven't seen that before. So now I have a way to find the cosine of an angle using the side lengths of the triangle. and I can substitute these side lengths into this formula to get the cosine of that angle. Now it doesn't really matter which sides are used for B and C, but it does matter which side I use for A, because that side has to be opposite the angle that I'm looking for. So in this case, the side A in this formula has to correspond with the square root of 17 because that's opposite the angle. So the cosine of ACB is going to equal B squared. Let's say B is the square root of 5. So the square root of 5 squared plus the square root of 10 squared minus A squared, which was the square root of 17 squared, all over 2 lots of BC. So 2 times the square root of 5 times the square root of 10. Okay, so now we've substituted everything into the formula. We just need to go ahead and solve this formula. So the square root of 5 squared is just 5. Same for 10, so this is going to be 5 plus 10 minus 17. All over 2 times, now the square root of 5 times the square root of 10, that's the same as the square root of 5 times 10, so this is going to be the square root of 50 on the bottom line. And so let's keep simplifying. 5 plus 10 is 15, minus 17, that's minus 2 on the top line, and 2 root 50, square root 50 on the bottom line. Now I can cancel those 2's, so I end up with the negative 1 over the square root of 50. Then I need to rationalize this fraction, so I multiply it by the square root of 50 on the square root of 50, which is the same as multiplying by 1, but the result is that I get rid of this square root on the bottom line, which we prefer to do in mathematics because it's simpler. So we end up with minus the square root of 50 over 50. And we can simplify this further. I might just bring this down to the next page, so let's just continue down here. So I can break the square root of 50 up into the square root of 25 times the square root of 2 over 50. And this becomes, the square root of 25 is 5, so I've got minus 5 on square root of 2 on the top line, and 50 on the bottom line. And then we can cancel the 5. And if I divide 50 by 5, I end up with 10. So this becomes negative square root 2 over 10. So the cosine of angle ACB equals negative square root 2 over 10 in its simplest form. So there you go, just a few vector problems to help with your revision. I hope you found that useful. I'll link some more problems in the description if you want to go ahead and have a practice by yourself. Leave a like if you did find that useful, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.